let's start talking about some things where let's think computers that let's think that computers can think as humans, alright, and they can think by something which is called neural networks. We're thinking that is not at all similar how we think, alright. So these computers have layers of tiny brain cells that can help help them learn things. So imagine you are trying to teach computer to recognize pictures of dogs and cats. You want computer to look at the picture and you want computer to figure out if it is dog and cat, and you want it to tell you which is which. So the first layer of brain cell will be looking at the picture and try to decide if it is a dog or not. If this is like a special filter that helps computer understand what picture looks like. The second layer of the output from the first layer. Second layer takes the output from the first layer and decides if it is the cat or not. These layers are like little math problems that computer needs to solve. The problem we are talking about today is called gradient descent. It's like the way for computer to learn how to do math problems better. Let's start with first layer, which looks at the picture and tries to decide if it is dog or not. The computer has something called weights, which are like special numbers that help it understand what picture it is. These weights are like arrows pointing in different directions. So if we take the 3D space, let's imagine these things are x, y, and z. Then imagine like these are the weights, right? So they are in different spaces, like different, they're on the different locations in the 3D or multiple dimensional vector space, and that they are in such locations that they form certain patterns in some kind of, if you train model in some way, and the shape of those patterns will be like, yeah, this model knows about such thing, that model is expert, that neural network is expert in French, or that neural network knows how to translate from German to English, or that neural network is fluent in Spanish, or even that neural network can solve mathematical problems much better than this one. So it all comes down back to the shape of the locations where these things, these weights are located at. So get this concept clear. So computer uses these weights to do my problem. It says if I look at this part of the picture and if I multiply it by my weight, how does that change the answer? This math problem is like little equation that helps computer to understand what's going on. The computer then adds up all the answers from each part of the picture and looks at total. If the total says dog, then first layer was correct. If it says cat, then first layer needs to be adjusted. This is where gradient descent comes in. Computer takes the answer, whether it is dog or cat, and it uses it to adjust its weights. It does this using another math problem that says if I multiply my weight by the number, how much will that change the answer? The computer then adds up all these numbers and sees if adjusting its weight helped improve its answer. If it did, that's great. If not, it adjusts its weight again. Now let's talk about the second layer. So the layers which we are talking about, they look like these, alright. So these are our layers. They are interconnected with each other like these, and we cannot understand exactly what happens between those, because that's some mathematical magic happening in the inner part of those things. So Yeah. So that's our basic neural network, like true layer neural network. So this is sigmoid. These are activation functions. These can be different activation functions. And yeah, I'm hoping the image is getting clearer. So problem with this is that computer might be getting confused between dogs and cats because of its weights. That's where the back propagation comes in. It is like a way for a computer to look at its mistakes and figure out why it's making them. Let's say a computer thought the picture was cat, but really it was a dog. The second layer would send error message to first layer. So something will go from here to here, and it will say, "Hi, hey, I made a mistake. You were supposed to telling me it was a dog." Then first layer can use that feedback and adjust the weight and try again. So that's what is happening all over again and again. That's where we say, yeah, neural networks are training or something. So the computer does this math problem so many times until it gets it right. So this is how neural network learn and get better at recognizing dogs and cats. Here's where we get into some more complex maths. But don't worry, I'll explain it in a way that makes sense. So let's say the first layer has weights A, B, C, etc. And these numbers are multiplied by different parts of the picture. So let's suppose these things are A, B, and C. And the second layer has G, E, F. And to adjust the weights, we need to figure out how much each weight is changing when we change one of them. So this is where my problem comes in. If I multiply my weights by the number, how does that change the answer? We use fancy math concept called partial derivatives to solve this problem. So it is like taking step-by-step process to say exactly which weights are causing there and why. Then computer then uses these partial derivatives to adjust its weights and tries again. So this process is repeated many times until computer gets it right. So basically that's how gradient descent works. Computer is trying to find the best way to understand what the picture looks like by adjusting weights and using math problems and from feedbacks from its own mistakes. So these six equations I listed earlier are like set of instructions for computer to follow. So the first one is check total answer from first layer. Second one is multiplied by the weight of second layer. Third one is subtract the original answer if any. Fourth one is check the derivative or partial derivative of that result with respect to the weights. Fifth one is add up those all derivatives across the all layers. And sixth one is use all those results to adjust weights. These equations will help the computer to figure out how to make these answers better and better until it gets them right. So now let's dive into the mathematical part of the whole thing. So basically let's go to complete where were we? Gradient descent, right? So yeah. So let's go to some mathematics. So single hidden layer. So we'll be having W1, B1, W2, B2, and X will be equal to N0, N1, and 2 equals to 1. Then the next one will be N1 and 0. The next one of that will be N1, 1. The next one of that will be N2 and 1. The next one of that will be N2, 1. So the cost function will look like j of w1 e2 w2 v2 all equals to 1 upon m. So I'm writing that down, 1 upon m summation of n I equals to 1 to n loss function y hat on y, where this will be equals to a of 2, right? Then gradient descent will be keep repeating these things. So the explanation of what I was talking about just like few moments ago, that's what this thing is. So I'm just writing the math. So we're going to compute predictions. So y hat I minus 1 up to m. Then we're going to have dw of 1 equals gj db of 1 will be equal to dj db of 1, and that will keep going on. And we are going to write w of 1 equals to gj dw of 1 db of I equal to gj. Then we are going to write w1 this thing. Similar for w2. v2, and this is for like true layers. We will be having like a lot of these iterations in the gradient descent, so keep that in mind as well. So that's how it is working in the background, for complex mathematical part. So formulas for computing derivatives, right? So let's get this thing. C1 equals to w1 x plus b1. A1 equals to g1 c1. Then g2, so it will be similar. So g2 will be w2 a1 plus b2, then a2 will be g2 of c2. That will be equal to sigma of c2, right? So these are activation. So we are going to go back to this. So when I was talking about the neural network or the neuron going back and telling them this was not CAM, this was not dog, let's adjust our weight. So this is how backpropagation. So that thing which I was explaining, this is how it is working. So g of c2 equals to a of 2 minus y. Then y is equals to y1, y2 until y of n, and g of w2 will be equal to 1 upon n, g of z to a1 g, then gg of 2 will be equal to 1 by n, and we sum dc2 axis equals to 1 keep dreams equals to time. So why we write these keep dreams that if we don't write, then we will getting the funny errors that will be looking like n comma something, or after that we'll be getting these arrays like n comma 1 step arrays. Then that's what it was. So we need to write that. So after that, so this multiplication sign has some meaning. So um, let's go over some iterations for how 6 equations for a backpropagation algorithm were derived. So please free to watch that or not, but either way these algorithms will have correct inclination of forward prop and back propagation. So we'll be able to compute the derivatives in order to apply gradient descent and learn the parameters for the algorithm. It is possible for implementing this algorithm and get it to work without deeply understanding the calculus, and that's what my goal is, to make everyone understand neural network, deep learning. Even if you guys don't know much of the calculus or much of the mathematics, or in that case much of any knowledge of things that you need to learn for deep learning. So just going back to what we learned quickly so you guys can maybe take notes, and yeah, that's all for this one. See you guys in the next one.